All right, yesterday we looked at the formation of sp3 hybrid orbitals, where we took the s orbital and all three p orbitals, mashed them together to make four new orbitals that are sp3 hybrids. The value of doing that, remember, is that they form a tetrahedron. Each of the 1, 2, 3, 4 hybrid orbitals points to the corner of a tetrahedron, which agrees with the tetrahedral geometry we see in experiments. And so we assume that the central atoms must be forming these hybrids because it fits the observations. In this example from yesterday, we used oxygen atom to make a water molecule, and we saw that two of the hybrids had lone pairs in them. The other two hybrids had open spots to bond onto a hydrogen or whatever and form, in this case, a water molecule. Now, let's look at other shapes. How do you get trigonal planar? Well, that's not going to work with these. What you got to do in that case is make a different hybrid. Take the s orbital and only two of the different p's and leave the other p behind. So that's going to be an sp2 hybrid, which you'll see on the next slide. So you see here, not even worrying about what electrons are in there yet. S orbital, the three different p orbitals. Now, in this case, we're going to take the s and only two of the p's and merge those three orbitals together. Now, that gives us three brand new orbitals. Those are the sp2 hybrid orbitals. sp2 because they come from an s and two p's. Now, notice that last p that we didn't mess with, it's still there. Of course, in this sample molecule, it remains empty. No electrons go in there, so we don't have to care about it. If we had time, I'll show you a case where that actually gets used for something. But you do want to be aware that leftover piece still does exist. Now, when you form these three sp2 hybrids, they look very similar to the sp3 hybrids. They're a big lobe on one side of the nucleus, a little mini tail on the other side that they don't show. But this time, they're arranged in the corners of a triangle. So these like orangish brown orbitals, 1, 2, 3, those are your sp2 hybrids, and you see how they're forming a triangle kind of coming out of the screen at you. Notice here's the leftover p that's in gray that doesn't get used. Now, since we had in this particular example, they used boron trifluoride, boron's s2p1. There's 3 electrons. When we rearrange to form our hybrids, 1, 2, 3 electrons go in the hybrids following Hund's rule. So each hybrid has 1 electron. The p orbital has none. And so when it bonds on to another atom, in this case they use fluorine. They could have used hydrogen to keep life simple. I don't know why they didn't. But the hybrid orbital right here bonds with fluorine. The one back there bonds with fluorine. The one up here bonds with fluorine. And you get a trigonal planar shaped molecule. Now, we got that from VSEPR. The added knowledge we have here is there's a leftover p that's poking through that trigonal planar that we didn't know or care about in VSEPR theory. But again, it's going to sometimes actually come into play. By the way, the f orbital, this is the f fluorine, let me try again. The fluorine atom here, they're showing a p orbital of the fluorine atom that's bonding onto the hybrid. Because fluorine is s2p5, right? So the p orbital is going to do the bonding. In reality, we could talk about the fluorine hybridizing too, but since it's a terminal atom, we don't have to care about that. Now, so you'll see, by the way, if I had an extra electron, I could put it maybe in here as a lone pair and just get an angular molecule. So all the trigonal planar base shapes, trigonal planar and angular, you can get that from sp2 hybridization of the orbitals. What about linear, you may be asking? Who wouldn't? Well, that's going to be sp hybrids. Now we'll take the s and only one of the p's, leaving the other two p's alone. So now we take the s and one of the p's, we put 2 orbitals in, we get 2 orbitals out. Those are called sp hybrids. There's only one s, there's only one p. And then notice the leftover p's still exist, and in this example, again, we're not going to use them. So they're making beryllium chloride. Beryllium is 2s2, nothing in the p orbitals. When it hybridizes, those 2 electrons get spread out. Remember when we did Lewis structures and I said spread out the electrons even though they are normally paired up in an s2? This is why. Yeah, the atom floating around alone in space is in an s2, but when it's going to get involved in bonding, it rearranges to a hybrid like this, in this case sp hybrids, and the electrons get split up. And so, notice, here's the beryllium, one hybrid with its electron, the other hybrid with its electron. Each one's going to have a little nubby tail that they don't show. Now, notice here's a p orbital, here's a p orbital. So there's one of them, there's the other one. Those leftover p orbitals poke through the line defined by the hybrids. Again, in this case, both p orbitals are empty, so we don't have to care about them. Now, a chlorine atom can come in and bond on right here, as you see over on that side, and another one can come in and bond in right over here on this hybrid, as you see there. So, each hybrid is going to be a bonding site again, and in this case, since there's only two of them, they end up on opposite sides or linear shape, and so that's going to agree with all our linear geometries you saw in VSEPR. Okay, so that's hybrid orbitals, at least for 2, 3, and 4 pairs. The linear shapes, the trigonal planar, and the tetrahedral. If you go beyond that, well, now remember you had expanded octets. And expanded octets work because you pull in the extra d orbitals. So for these, we had sp, sp2, sp3, using all the s's and p's. To go to expanded octets, we're going to have to throw d's in there as well. So here's just a rundown of the whole thing. Linear gives you sp hybrids, and 2 of the p's are left over. Trigonal planar gives you sp2 hybrids, 1 of the p's are left over. In this case, the p is poking right out of the page at you. Tetrahedral gives you sp3 hybrids, and you've used up all your p's now. If you have a trigonal bipyramidal shape, or anything based off that, like seesaw or T-shaped or all those, then you're using your S and your 3 P's, but you're also using the D. So you get an sp3d hybrid orbital. Now, the rest of the D's are left over, but who cares about those? If you have octahedral shape, you're going to have to use 2 D's, so you use an sp3d2 hybrid orbital. These hybrids are a little more complex, obviously, but they exist. So, here's the thing. How do you know what hybrid orbital is going to be used? You have a molecule. I ask you, what hybrids does this central atom have on it? Well, you can't really predict it ahead of time. What you have to do is, number 1, draw the Lewis structure. 2, use VSEPR to figure out the shape. Once you know the shape, then you can go here and say, oh, it's tetrahedral, must be sp3 hybrids. In other words, you base your hybridization on the shape you know it has to have. It would be better if this hybridization model would just, on its own, tell you, oh, since this is the configuration, it must obviously do that hybrid. This model doesn't do that. It only works kind of after the fact. Once you use VSEPR to get the shape, you can then deduce, oh, it must have been these hybrids. And that's really what the next slide is saying. How you figure out the hybrid orbitals, draw the Lewis structure, use VSEPR, and then based on the shape, you know the hybridization. Now, we have a little time left here, so I want to talk briefly about double and triple bonds. I'll show you this here, sigma and pi bonds, although I want to draw pictures. These aren't very good. A sigma bond is when the electron cloud overlaps between the 2 nuclei, one nucleus, the other nucleus. So, when electron clouds overlap, normally they overlap right here between the 2 nuclei, and they form a type of bond we call a sigma bond. When s orbitals overlap, they do that, so the Greek letter S is sigma. That's why we name it that. Now, a pi bond happens when p orbitals overlap sideways. So here's an atom right there is the nucleus with its p orbital. Here's another atom with its p orbital. Notice if you bring them close enough together, the p orbitals overlap, not in between here, where you would expect a bond to be, where a sigma bond certainly would be. The overlap occurs above and below the plane of the bond. That's called a pi bond. So again, nucleus here, the bond axis is right along here, but the electron cloud isn't there. The electron cloud is above and below that. Again, it's called a pi bond. The Greek letter for P is pi. And so those two types of bonds, Oh, okay, so here we go. I do have some decent pictures in here. Notice now, this is the ethane molecule. Carbon bonded to carbon, and then each one has 3 hydrogens on it. So I want you to see, oh, okay, it's CH3 bonded to CH3. Okay, now notice, since it's tetrahedral overall geometry on this carbon and on that carbon, you see that, right? Each carbon is the center of its own tetrahedron, and they're stuck together. Now, the hybrid, sp3 hybrid, overlaps right here with the other carbon's sp3 hybrid. You see how they overlap right exactly in between the 2 nuclei? That's a sigma bond right there. The carbon to hydrogen, well, the overlap is right here between the 2. It's another sigma bond. Now, what they're showing over here is the electron cloud being more or less evenly distributed around the molecule, because they're all sigma bonds. Now, I want to do this quickly because I don't have a lot of time and I don't want to spend another day on this. Let's put a double bond in there, the ethylene molecule. Now, it's C2H4, so CH2 bonded to CH2, and when you do the Lewis structure, you're going to find out it needs a double bond. Now, notice it's trigonoplanar because there's 1, 2, 3 groupings around the carbon. That means sp2 hybrids. So here's the carbon, hybrid, 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 forming a flat triangle, leftover p. Now, carbon has 4 electrons, 1, 2, 3, 1 in each hybrid. 4, the 4th one goes into leftover p. Now, you see how the 2 carbons, their hybrids overlap? The overlap occurs right there between the 2 nuclei. That's a sigma bond again. The carbon to hydrogen bond is sigma. The carbon to hydrogen here is sigma. All of those are. But look at the leftover p for this carbon and the leftover p for that carbon. Each one has an extra electron in it. So those 2 electrons can overlap each other. The p orbitals overlap. Now, they stretched it here. In reality, they'd have to get closer together, obviously. But they just stretched it here so you can see it. The p orbitals overlap, and the bond forms above and below like this, kind of around the whole thing. The center between the nuclei is in here. The bond is above and below. So this darker colored bond here is a pi bond. Sometimes people mistakenly think there's one pi and then another pi. Nope, it's all one big p orbital set. So that's one pi bond that I'm circling around there. And then there's also one sigma bond right in here. So you see how the carbons are held together by 2 bonds. They're held together by a sigma bond, and they're held together by a pi bond. The carbon to hydrogen, there's a sigma bond, and that's it. There's no pi bond, so it's just a single bond. So right there's a single bond. Here, it's a double bond because you got your sigma here, which they show just as a dash now, and your pi above and below. Again, that's all one big pi bond. Now, if you look at the electron cloud, red means more electron density. You see how there's greater electron density above and below? That's because of the pi bond. Now, notice, by the way, those p orbitals have to line up. If you twist this so the p's don't line up, the bond breaks. That means double bonds are rigid. A single bond, the atoms could rotate around that. So if I go back to that, these 2 atoms can rotate around that bond. So if you look at this, those hydrogens on the end are spinning like a propeller blade because you can rotate around this bond. But with a double bond, you can't do that because if you did, the p orbitals wouldn't line up and the bond would break. So this is rigid. These atoms are locked in place. They can't just spin around the bond anymore. And when you get to organic chemistry, you'll see some important things happen because of that. Some types of isomerization. In my last minute here, real quick, if you form a triple bond, you form sp hybrids. So here's your carbon, sp hybrid, other sp hybrid, leftover p above and below, leftover p in front and behind. It's kind of hard to see. The hybrids overlap to form a sigma. You form a sigma to your hydrogen over here. The up and down p's overlap to form a pi bond, and the front and back p's overlap to form another pi bond. And so you see how you get a sigma bond in the middle, they show as a dash, a pi bond in front and behind, and a pi bond above and below. So that's 3 bonds. That's a triple bond. And that's all we're going to be able to do with bonding. let's end it there, and then we'll move on to some new stuff after this.